Hello, welcome to section 4, multivariate normal distribution. The multivariate normal distribution, it's good to learn because it uses many concepts from probability and linear algebra, and it combines them beautifully. So you get to synthesize multiple ideas into like one coherent concept, which is the multivariate normal distribution. Um, it's It's used heavily in multivariate regression and machine learning. So it's something like really good to know. Before you actually look at this module, please review uh, linear algebra concepts, section 4, and used in statistics and machine learning. Okay, so a lot of this will be using the concepts from this particular module, and it would be good to review it at this time before you proceed. So the multivariate normal distribution is a generalization of the one-dimensional univariate normal distribution to higher dimensions, okay? So it's not just one normal distribution, it's one, two, three, depending on how many you want. So it could be any amount. In a univariate normal, you have one random variable, whereas in a multivariate normal, you have multiple random variables, as the name implies. So each of them could be correlated with each other. So here's the write-up of the mathematical expression of the multivariate normal distribution. X is a vector. I mean, now instead of a single number, it's a vector, right? Mu is a mean vector. This summation symbol, I know that people could be confused thinking that it's a summation symbol. It's not. And in mathematics, they tend to use these Greek symbols and for multiple purposes. That's because the Greek alphabet is limited. So this is basically a covariance matrix in this case, which we covered in linear algebra. D is the dimensionality of the random vector. The absolute value of the covariance matrix. I mean, this is not, again, this is not the absolute value, but it's the determinant of the covariance matrix. The T here is the transpose, which we saw, and the -1 is the inverse of a matrix, okay? So that's the covariance matrix. If you look at this piece by piece, you'll get a better understanding with the description here below. So like a quick interpretation, the mean vector mu represents the average value of each random variable. So in a two-dimensional case, we have mu1 and mu2 represents the average value of variable 1 and variable 2, okay? The covariance matrix describes the relationships between the random variables. It includes both individual variances of each variable along the diagonal, and we've seen this before. Sigma 1 squared, sigma 2 squared, these are the variances and these are the covariances, okay? And recall that that relationship, these are equivalent. So they should be equal on the off diagonal. Understanding the multivariate normal distribution has been essential for statisticians and machine learning practitioners for effectively modeling, analyzing, and making predictions about complex data sets with multiple correlated or uncorrelated random variables, right? Just a quick note, if it's highly correlated variables, you're probably getting information that could be redundant, right? If they're highly uncorrelated, then basically you have non-redundant information, right? This is minus the idea of causation. Let's just talk about the strict mathematical definition of correlation. If it's 0, there's no correlation. If it's 1, it's perfect correlation. In two independent normal distributions, the covariance matrix captures, right, the dependencies between the two normal distributions, right, sigma 1, sigma 2, okay? If normal distributions are independent of one another, right, the covariance is equal to 0, okay? So that's what we have here. The covariance will be 0, so these two variables are basically independent of one another, right? I think I gave a regression example in the linear algebra talking about income, right? Like job and age, age and income they could be somewhat correlated, right? It's not new information, okay? But maybe job and income, those two might not, well, those two are correlated as well, right? But what about something like location and income? They could be two independent things, right? Just because you work in two different locations doesn't mean necessarily that that will highly correlate with the income you make, right? But maybe job and income would, right? I mean, a doctor would probably make more money than a, you know, a a you know, engineer or whatever. I mean, like a teacher or something like along those lines, right? So independence is a important attribute in the sense that it's there's new information. Okay. When it's correlated, it's redundant. That would be the practical implications of something like looking at two independent variables, right? Here I give a Python example to kind of demonstrate that, right? An independent and a correlated and an independent multivariate normal. And you could kind of see what happens, right? If it's correlated, it's basically moving together. If it's independent, it's basically there is no movement together. I mean, it's basically bounded by this bounds, and there's no special relationship that one can infer. Here, you can infer that X and Y, they move kind of like in lockstep, right? So age and income would be probably correlated, right? I mean, the older you get, the probably more money you make, right? So that's basically it for this section. We're going to wrap it up. Thank you very much, and I'll see you in the next section.